seminar, we have the pleasure to welcome Nathanail from the Academy of Athens. And Antonius will talk about how to extract energy from a rotating black hole. So, as usual, feel free to ask questions. There will be some time at the end as well. And Antonius, thank you very much for being here, and you have the floor.
Thank you. It's a pleasure to be here. As Jordan said, I will discuss about how to extract energy from a rotating black hole. I mean, the whole idea is about magnetic fields and black holes. I don't know if other mechanisms people believe are working, but I will be focusing in the Planck mechanism. I will discuss about its foundation, why you can extract energy, why you can have all this energy flowing outwards and inwards. I will then go to mad accretion, which is magnetically arrested disk accretion. It's really important in astrophysics. We use it everywhere. We believe it can explain a lot, but not everything. And then I go to negative energy plasmoids. I want to go a bit to magnetic reconnection close to a black hole. And again, how you can extract some energy and some ideas from this. So let me begin. Usually people say mass, spin, charge for the black hole. Here in this room, maybe I don't have to discuss about Noether theorems and stuff like this. But I just want to, just stick a bit to the charge. Only for 1-2 slides, and I want to say that astrophysically, I don't know what people believe. Usually, people believe that the charge is negligible or it doesn't even exist in black holes. But astrophysically, what we managed to do some years ago is to have a collapse of a rotating neutron star and show that at the end the black hole is charged. So here in the colors, I show this quantity here, which is I have here B and E, and this is just in a 3+1 formulation, just to have an idea electromagnetically how you can see it, but it's just this contraction of F nu. And in the colors, you see that white is the zero. This is the initial condition. It's just a neutron star which is not rotating. This is the surface of the neutron star, and this is the magnetic field inside the star and outside the star, the whole magnetosphere. You see that it is red, so it is magnetically dominated due to the magnetic field. As it evolves, here you have the collapse. You see that you have this whole ringing down of the space-time. All the mass goes inside, and the magnetic field continues to be perturbed and fly away from the black hole. And at the end, you are left with a kind of zero of this quantity, so you are not magnetically dominating, not electrically dominated, and the magnetic field continues to ring down, and you will lose all your fields at a certain dynamical time scale. So this is 3 or 4 milliseconds after the collapse. We trigger the collapse by overpressuring, so you have initial conditions. This star initially can stay there for a long time. And but we just overpressurize a bit in the surface of the star to trigger the collapse, and this is the idea. But when you have,
sorry, you still have that red semicircle.
So this is the apparent horizon. This is numerical relativity simulation. So you try to find, and this is the horizon of the black hole.
So it doesn't mean there's magnetic field there, because that was looking just like.
No. It's just the apparent horizon.
Ah, I see.
No.
It's the color, right?
Yeah. Sorry. It should be dark, I don't know, or black.
Some other color.
Yeah. So it's not magnetic field. No. So now, a different initial condition. This is the period of the star up there, 2.5 milliseconds. So it's highly rotating, a kind of large magnetic field, just that we can measure the charge after the black hole. We expected that a charge will be there. So again, the same situation. You have a rotating neutron star. If you allow the solution to stay there for a long time, you will just have a rotating dipole. But then we just trigger the collapse. And when the collapse is out, all the matter goes inside, behind the apparent horizon, again in red here. But you see that regions of electrically dominated are produced over there, and after the ringing down, you are left with a totally electrical dominated region. And now if you integrate the charge from the black hole, you have a non-negligible value, and the space-time, so that we say that it's a Kerr-Newman solution.
What's the charge to mass ratio?
I don't remember. I haven't seen this study for years, but I would say 0.1 or 0.01 or something like this. It's very small, but it was just a proof of concept that we can have a neutron star collapse the black hole and has a charge.
Okay, but so typically the argument is that you start with something that's approximately neutral, and then it will discharge because it will absorb the opposite charge. But I guess in your initial conditions here,
if you can have these charges outside. So if you don't have charges, so for example, you can have pulsars that have charged starred magnetospheres, so there are no charges available out there. And if you have this situation, you cannot accrete any charges.
but these magnetized neutron stars you start with, they have a total electric charge which is non-zero, or is it just a kind of a dipole magnetic field?
It's a kind of so it's a dipole magnetic field alone, and from this dipole magnetic field, as it rotates, if you integrate, the charge on the surface of the star, you see that the star initially is charged because it's working. If you break it, there is no charge. It's just an induced charge.
I see, because on the Earth you have a magnetic field, but the total charge is essentially zero. Right? So you're saying that it's different in the case of the magnetized neutron stars.
In the case of the magnetized, you can have a different solution. You can put the magnetic field solution and electric field solution initially that you can have everything like this. But people believe that pulsars, active pulsars spinning down, have a charge. Yes, due to the rotation and the magnetic field. It is an induced electric field from the rotation, and at any time, the pulsar is polarized. I think maybe electrons go to the pole, and maybe positrons.
But again, the total charge will be zero, no?
No, you have an extra. So this is the polarization of the star. You have an extra component of the magnetic field, and now if you integrate all of this, you have an extra charge. You always see an extra charge when it is spinning. If you stop it, there is nothing, you will not see anything. It's an induced charge due to rotation. Yeah.
But it forms somehow from a neutral star that magnetized with non-zero charge.
So it's a game about what is the magnetic field and the initial fields.
Right. I think it's about initial conditions.
Yes.
So if you set an initial condition with a total non-zero electric charge, that might be self-consistent. But the question is, how do you form it?
How do you form an initially no charge? Yes.
To see what's because the same argument would sort of apply if you start with a neutral star. And then if you actually get a region where there would be an excess electric charge.
So if you go really far from everything and you integrate, I think the net charge is zero always, even in this configuration.
But we can keep on the discussion again.
So the black hole, the end final black hole would be charged, but also the magnetosphere would be charged. No? So,
with the opposite charge?
That's what
Why would it be discharged then?
No, the opposite charge is at infinity. It's not that it is in, 20 kilometers, or if you think in RG, it is in 510 RG. It's not like this. You can integrate the charge, if you integrate, for example, the Goldreich-Julian charge density, you will see, you can play with this charge initially, what you have outside in the magnetosphere. So you can have a magnetosphere which is Goldreich-Julian, so E.B is always zero when you have this charge, or you can put zero charge outside, and then your star is charged. So if you assume that plasma processes, you can have percreation and you have all these available charges outside, then you cannot produce. You will accrete everything, you will not have. But here we put outside electrovacuum, so we put no charge outside.
I see.
So you cannot accrete anything from outside.
It's your initial condition in some sense.
And it's just from some stars that they believe in pulsars, they are just charged-starved magnetospheres, that there are no charges outside.
Right. Okay, but here you're starting with a magnetic, a neutron star with some charge, if I understand that correctly, and you end up with a black hole with some charge.
Yes, but it's not that I don't put a Q, I put a magnetic field.
Yes, so I understand there is a reconfiguration.
Yeah.
But what I was trying to map is the total electric charge in the initial and in the final. What I was interested to know is if you could start with something that is a neutron star with total zero electric charge. And somehow the dynamical process would favor the creation of a human black hole with non-zero charge. And by some mechanism to get rid of the opposite charge to infinity.
Yeah.
That would somehow be adding on trivial.
I can check the initial condition. I mean, I just wanted to put some for the charts in this talk. I haven't thought of this for.
But sorry, we can do on that line or something. Yeah.
Okay, so going back, going further. So all of the black hole parameters, but what I want to say, I mean, in this talk is that magnetic field is really important, and astrophysically, it's really important how you will see the black hole, if you will see the black hole, if you will see a jet, if you will see the disk around, and how you can put all this together. So I will discuss about the Flanders-Snide mechanism. Here is an illustration, event horizon, accretion disk, and this relativistic jet there. This does not exist. Okay, you cannot have accretion disk and this expensive jet over there. Okay, the magnetic field doesn't want to produce something like this. It can produce jets, but not like this. The important thing always that I will stick is this. This is the power of the Planck-Snide mechanism. This is the power of energy, let's say, that you take from the black hole, and it depends on the rotation of the space-time and the magnetic flux that you can accumulate at the event horizon. This is this phi here. Okay, so if you can bring magnetic flux to the horizon, then you can build solutions that you can extract energy, and I will try to go a bit theoretically in these ideas. Okay, the Pulsar equation, this will come. I will start with electrovacuum solutions, so outside there are no charges. Okay, this is a black hole, and you just embed it in a vertical magnetic field. Spin is zero, nothing happens, everyone is happy, the black hole is there, then the magnetic field is there. I don't want to discuss what happens very, very close to the horizon. Okay, but this is, let's say, if we are outside the picture you see. Now we start turning the black hole more and more, and you see that if I go to spin 0.9, the field lines want to bend a bit, kind of want to go away from the black hole, and this is due to rotation. This is really close to the famous Wald solution from, I don't know, the 70s. And you, again, through rotation, you induce an electric field, and this is what makes these field lines bend like this. Now, if you go to even more extreme values, 0.999, you see that the whole of magnetic flux is going outside from the black hole. So the black hole is rotating, the magnetic field is going out from the black hole, you cannot produce jets, you cannot produce anything. So the only way to start thinking astrophysically, realistically, you need charges, you need plasma around, and this can produce currents, and this can turn the magnetic field, you can have the B5 component, etc., and you can have a solution. So if in this solution, I just throw as many plasma as I want in this configuration, I will really quickly arrive to this configuration. And I will, let me take some time to discuss what this is. So this is the static limit, the limit of the ergosphere, and inside is the inner light surface. I will discuss later a bit more in details. So what you see here is that all field lines, when they touch this inner light surface, they really strip off and they go to the horizon. Okay, if you are inside the ergosphere, but you are not touching the inner light surface, you don't care. Because the space-time is rotating, the field lines, these field lines rotate. Okay, but they don't bend, they don't produce B5, these solutions. Each field line that passes the inner light surface, you are producing an electric current, and all these field lines that go here are like this. So if I go and take this picture in 3D, okay, outside I have a solution of magnetic field, which is just vertical, just do not give you any energy. All field lines that come to the event horizon are twisted like this, and they have a pointed flux. Okay, if you integrate, there is somewhere there a surface that from above pointing flux is going outwards. From inside, negative pointing flux is going towards the black hole. And this is what we believe is making the black hole to give the rotational energy and spin down. Okay. The inner light surface, let me close. So the inner light surface, I write there is a unique feature of black hole Magnetic surface. It marks the boundary where plasma is forced into co-rotation by intensity dragging, and you exceed the speed of light. So if you have an idea, so in pulsars, so if this is a pulsar and I have a dipole field, it's this region here that is called the light cylinder. And if you have a certain velocity, at this distance, your velocity becomes the speed of light. And this is the light cylinder. So if you want to co-rotate with the star, and if you have a field line passing like this, then here, any plasma, any charge that is stuck on this field line will move with the speed of light. That's why pulsar solutions, they go like this, and then here they open up. Because anything stuck on a field line cannot remain here and start moving around the field line, so it is producing electric current. This is producing these open field lines, and you are taking energy from the pulsar to infinity. This is a similar thing, but this happens, this is a GR effect, and it happens inside the endosphere. So here, if you co-rotate, you are moving, you are exceeding inside this inner light surface the speed of light. So now you cannot be co-rotating in here, and you start flowing around. Depending on your sign of a charge, an electron or a positron, you move in the other direction and you produce an electric current. And you produce all these field lines now have electric current, and outside you have a toroidal field, and you have a current close exactly at the last field line. It's the electric current closes. Okay, this is the Egger field. Okay, some equations. Maybe I don't want to spend some time, just a 3+1 formulation, and how you want to solve this equation. Just I wanted to say here that if you just put the mass and the spin to 0, it's just the pulsar equation. Okay. It's just the pulsar equation, and this in front is where you have the light cylinder. And if I go back to the other, this in front is where you have two light cylinders. The standard light cylinder, which is far from the black hole, and then you have an extra surface, the inner light surface, that gives you all these nice solutions. Without this GR effect, you will never have the opportunity to produce electric current. You will never have the opportunity to make this outflowing pointing flux and take some energy from the black hole.
So when you say that it moves with the speed of light, you mean by with respect to an observable infinity, you
Yes.
see that they are still time-like trajectories, I guess, because
Yes.
it's still plasma. But
Yes.
with observable infinity, you measure that or see that.
This is the observable infinity, but also this is a place that the whole equation breaks down, and you have to pass. It's like a singular surface in the problem. And this, I mean, in the standard Blandford-Knight formulation, I mean, you can see that it's a singular surface. So something is going on there, but you don't know what is going on. So to the black hole problem. Now, if I put magnetic field to a black hole, this is the outside, the light cylinder, as you have in pulsars. So if you co-rotate, a magnetic field line co-rotates, there, if you pass this light cylinder, you want to open up. Again, this is the static limit, and inside is the inner light surface. You see that if I put just an electric current here that stops the magnetic field just wants to fill the whole space. So the black hole and the magnetic field does not want to build jets. Okay, the magnetic field is just filling the whole space. This is similar to the pulsar solution it doesn't want to produce jets. However, if you bring vertical magnetic field to the black hole, then you will have this electric currents, you will have this solution, and you will have outflowing energy. And again, you can confirm that this is the power of the jet, depending on the rotation of the black hole and the magnetic flux that you bring there. Now, if you play with different boundary conditions, paraboloidal or whatever, like it's the wind, the accretion disks around this star, if you are in a GRB, whatever is your situation, then you can collimate the magnetic field. But you have to put outside an agent that collimates. So that's why I was arguing this is not correct. No jet can be like this, and this is seen in numerical simulations also. Here the agent is the whole wind, the density distribution outside this really magnetized funnel. The field lines, the magnetic flux that can be at the event horizon, this is your solution. Now you have a slice, but this is a lot of toroidal field, and this is pushing everything. It's cleaning the whole funnel up and down. It's pushing everything to relativistic velocities. But the agent to collimate this jet, to have this nice jet, is always a density distribution, a pressure gradient, something from the outside that tells you what's the region that the magnetic field can fill in. Okay. So, till now, I mean, I try to convince you that you need to bring magnetic flux to the horizon, and then if you bring magnetic field to the event horizon, you will have an outflowing of energy. And now I want to discuss how, if it is important, how much magnetic field you are bringing. So if you are bringing some magnetic flux, low flux, you have a same. This is called standard and normal evolution of accretion. So you can have a jet, but you don't have extremes. Accretion continues. But as flux accumulates, if you have more and more and more, you find the saturation limit. This is called the MAD limit, the magnetically arrested disk, which means that I have brought as much as magnetic flux the system can carry to the black hole, and then it stops. It cannot bring more magnetic flux. In this MAD situation, you see that you have built this nice funnel. Accretion continues all the time. Accretion doesn't stop, but you have this nice funnel, and every now and then a large vertical flux tube is expelled from the horizon. So because you have reached a saturation limit that you cannot bring more, every now and then this magnetic pressure built above the event horizon is pushing a part of the solution outwards. And this is what you can see, this vertical bundle here. So here you can see this again in 3D. Again, you have built your solution. This is 3D GRMHD simulations. And you see you have the solution, and every now and then a flux bundle from the event horizon is expelled inside the accretion disk. And this is really important astrophysically because this happens due to reconnection events and can give you particle acceleration. You can energize the particles exactly at the foot point on this, and then these particles will drive on this flux bundle, and you can have flare events and stuff like this that you expect to observe. Even if we know these solutions from 2008 from Igumensev, these flux eruption events, still we are not sure why these things happening. So here I have equatorial slices in different quantities, and here in this quantity on the dark blue, the dark purple, each sign that you see here is a flux, is a vertical magnetic field. So all the magnetic field from the disk and the black hole is rotating, and it has this toroidal field. All these features that you see here are just vertical bundles that just pop up inside the accretion disks. So we are trying to understand why every now and then just some RG from the black hole, a vertical bundle just pops up and gives you these nice things for particle acceleration, etc. So what we think happens is that when you have this bundle, this initial field, which is everywhere rotating, coming really close to the event horizon, there are some conditions that are really close to the ergosphere tells you that I want to reconnect, and because the magnetic field wants to reconnect, you see a plasma, let's say blob, goes inside to the hole, and the other field is left outside. Now, if I continue our sketch, a plasma blob goes inside the event horizon, and then you are left with a vertical bundle, and this is what we believe is happening. We are trying more to investigate on this. It depends. So on the last column here, it's the velocity between the boloidal and the toroidal magnetic field. We believe that there are really close to the ergosphere some conditions that allow you to reconnect and build these bundles. Why all these are important astrophysically? So here is a bundle. Again, you have the accretion disk going around. The gray are field lines from the disk. The accretion disk is trying to bring all these gray field lines to the black hole. The golden ones are field lines that are exactly coming from the event horizon. And this red one is just a flux bundle. It was just expelled. It was just cut from the ergosphere. And it started out here. And this is just outside the main jet solution. So here, all this color here is an intense reconnection event that you have just seen, and this is how this was formed. Now, why this is important, or how we are trying to use it? Now I'm going to observations. These are observations from the gravity instrument. This is from Sagittarius A star. They believe that Sagittarius A star is somewhere in this big cross here. And they are looking in the sky, and they have this clockwise motion really close to the event horizon. So here is in microarc seconds. I think you have to divide this by 20 to have Rg. So this motion is around 3 to 6 Rg from the black hole, depending on where you put the black hole. So in time, you will see something here, and then you see this motion around the black hole. So they observed something really close to the event horizon, having a clockwise motion. So we are trying to model this with a MAD solution. We are trying to say, okay, suddenly a flux eruption event, so this flux bundle was formulated, and then suddenly there a lot of energetic particles were given energy, and they want to ride on the magnetic field. Now, if we take this model, this line with the axis is our model, so it is exactly this flux bundle as you see it, and we just put electrons to fly on this thing, and this is how you see this is 30 minutes around, moving around the black hole at the center of our galaxy.
Is there any information about the magnetic field around Sagittarius A star?
Any?
Information about the magnetic field?
There are some information, there are some polarimetric observations, but we don't know what it is. I will say in a while also for some EHT observations. So what we do with the EHT is we have numerical simulation and we try to fit the images. And no numerical simulation that we have today fit the image of Sagittarius A star. I mean, not the image, there are several constraints, I just don't want to go to details, but there is no accretion model nowadays that can fit all the details of the observations of Sagittarius A star. So we don't know what is exactly the magnetic field or the accretion mode really close there. But we are trying part by part. So one constraint is this gravity motion. So we're trying to see, okay, if it is a MAD model, if an eruption, can this fit? So this is.
Yeah, sorry, I also have a question related to this. So Sagittarius A star is not AGN, right?
I don't know, how do you define it? I would say it's an AGN.
Okay, well, maybe I'm wrong. I mean, that's why I'm asking. I was wondering. But it's not a very active one, right? So is there a jet also coming from Sagittarius A star?
I think that's an open question. So because we cannot really see, other people say we have evidence, we have seen a jet. Other people say that there is no jet. Other people say that there was a jet in the past, but now you can see further out the influence of the jet in the galactic medium. I think it's an open question. We don't have the resolution to see the base of the jet, to see really close to the black hole. And if we could see the base of the jet, maybe if there is a base or not, this could resolve this question. But
because for M87, it's star, it's clear, right? It's a very active.
For M87, it's very clear. And I think it was the first day that it was observed. I mean, it's this pencil-like. Yeah.
And I had another question. Is it just with MAD motors that these bundles can be ejected, or?
So whatever kind of magnetic field you bring to the horizon, you will make a Z. But the MAD model can have a powerful Z. So for example, for M87, you need a MAD to see, let's say, the energy that you see from the Z. If you have a lower energetic Z, then you cannot fit all the constraints of the Z. Let's say really quickly.
So I just have another question on this. So maybe this is not on your work, but on the gravity collaboration results. So I remember that it was at that time when these results came out for the first time, they mentioned that the motion was super Keplerian and this was hard to fit for Jeremy models and everything because we usually get Keplerian or super-Keplerian velocities.
Exactly.
So later I heard some other arguments saying that actually the motion is super-Keplerian, but because of the scale at which they look, it appears super-Keplerian when they do the astronomy. So first question is how to interpret this. So is the motion really super-Keplerian or is it something else? And second question is whether in this work that you cite there, whether you find velocities that match the observations of gravity.
Yeah. So to begin with, initially, if you just see the motion of this thing on the sky, and you assume it is on the equatorial plane, it is super-Keplerian. Okay, but it is this assumption that I have to model it, put a black hole spacetime, put a hotspot rotating around the black hole. If you want to fit these observations, then this hotspot is moving super-Keplerian. Okay, and this is correct. This was the initial from gravity and other groups, and they said, okay, this is going super-Keplerian, it's going really fast. GRMSD simulations are not going fast, they are sub-Keplerian, and this simulation is sub-Keplerian, so all the plasma, the accretion disk is sub-Keplerian, so how can you fit this? So Eleni, the PhD student from the University of Athens, before this MAD did the parameter study and saw that if you are outflowing, you can be sub-Keplerian, but because you are outflowing, the projection of the sky seems super-Keplerian.
So we are looking from the,
exactly.
from the top of the jet, let's say, and
you have a really small angle. You have a really small angle, viewing angle with Sagittarius SR, and then this thing is moving sub-Keplerian on this orbit, but because it's moving outwards at the same time, you have the impression on the projection of the sky that it is super-Keplerian. And from this parameter study, so maybe a MAD can work, because initially there are other studies that saying the foot point of this is going sub-Keplerian, so you cannot feed it. But if you allow the energetic particles to move on the magnetic field, which is, expected, then you see that it really fits and everything is moving. The whole bundle is moving sub-Keplerian, and the particles just move on top of the flux bundle.
And this also, I guess, limits the possibility of constraining the space-time by thinking that the hotspot moves in a Keplerian orbit.
What do you mean? How to?
Because there is a recent paper also of the gravity collaboration where they say that based on the motion of that hotspot they can estimate how much mass is inside. But if the particle or the blob that is emitted,
I suppose they have the assumption that they are stuck to the equatorial plane.
Right.
If you have this assumption, maybe you can make an estimate of the mass. But I think for the mass you cannot do it. What we are trying right now is we are putting viewing angles, different viewing angles at different spins from the black hole, and we think that you can pinpoint the spin of the black hole, assuming that this model works. Because with different spin, then you see that actually what is really interesting, the spin is connected with the toroidal magnetic field component. So if you have less spin, you have, let's say, bigger going lower. When you have a higher spin, you are more like this, and then you can go faster. And that's why we believe you can constrain the spin with this gravity observation, the spin of the black hole.
Can I make two related questions? Sorry to dwell on this one. So first, these are blobs. I guess when you're talking about Keplerian motion, it's geodesic. So is it clear, one, that they have to be geodesic motion. And two, when you talk about Keplerian, I guess you refer to Keplerian, like you told it, but you said
no, it has the GR correction.
Okay, so between 3 to 6 gravitational radii, if it would be a Schwarzschild black hole, we would be between 6 m, which is the isotope, so very close to the isotope, where of course the frequency is not Keplerian. So when you mean that Keplerian is relativistic, but then you have to know if you're in Schwarzschild or in Kerr. And because it varies, so you have to know the speed. So
I said a lot of things really like this. You have to set the spin, and then you know the Keplerian, and then you can say if you are the relativistic Keplerian, and then you can say if you are sub-Keplerian or super-Keplerian. So people, I think, in the beginning they had this data, and they put a Schwarzschild or a 1 Kerr parameter, and they say, if I want to go in 30 minutes for Sagittarius A star that the TG is 20 seconds, I think, the dynamical time scale, then I have to move really fast. I have to be super Keplerian.
Independently of the spin parameter.
Yes. In both, I think they had
independent of being co-rotating or counter-rotating, because it varies a lot in that case.
Yes. Well. I don't know if they have tried.
Oh, okay. Just
I mean.
And is it clear that this should be some sort of geodesic motion because it's a blob, right? So
yes,
it's an assumption, I guess.
Of course, it's an assumption. I mean, you don't know if it is a blob. You just saw some light here, some light here, some light here. Is it a blob? People say it's a hotspot because they can understand it's a blob and it's moving. It can be a reconnection event. I don't know. So you have a layer that magnetic field reconnects, and it is the I don't know, the electromagnetic information that I'm reconnecting that is moving, and not the actual blob.
It's certainly not the test point particle.
No. Okay.
Are you going to talk more about constraining the spin? So I think this is an interesting question.
I don't have new things to show.
But is there a degeneracy between the viewing angle and the spin?
The viewing angle, it's definitely a degeneracy, and you have a really small viewing angle to Sagittarius A star, or else you cannot have these things. These things just move.
But this is maybe not what I expected, because I kind of expected that Sagittarius A star would be rotating like the whole galaxy, and then we are more or less on the equatorial plane, right?
So why the black hole? You mean rotating like the galaxy? You mean
maybe this is a wrong preconception that I have.
So I mean, the people are really puzzled because we are focusing to two black holes, supermassive black holes, and both of them seem to have a really small viewing angle. Also, M87 is like this. But this is what the modeling is doing. Maybe something is wrong, but for example, for the viewing angle for this model, you have to really watch it from above. If you are starting, I don't have the plots here, so if this is the motion I'm trying to mimic, and this viewing angle is, I don't know, 10 degrees, if you go to 50, then this shrinks. If you go to 90, this is really like this. So, and the points are here. So if you go to really to this kind, so if you are looking from the equatorial plane, all this motion, whatever motion you have there, is really like this. You see it from this. So you cannot fit this motion. But of course, I mean, if you change the modeling, you tell me that I'm moving, I don't know how, maybe there is another interpretation. So to stay a bit for Sagittarius A star and the variability crisis, this is the image or what the HT showed. What I'm showing here is a distribution of variability. Behind this gray is a historical distribution of variability, and this is where MAD models go. So even if all MAD accretion models can fit all constraints, the image, whatever constraint for the, if you expect exact power, the near infrared, optical, all constraints, it cannot pass the variability. So all GRMHD models are a lot more variable than Sagittarius A star. So still, I mean, the question is open. We don't know the accretion model of Sagittarius star or the magnetic field. For M87, I mean, this is the initial picture. This is the GRMHD, GRRT, I mean, radiative transfer in general relativity. If you blur it a bit, you see how easily it matches the image that we see. Again, the EHT collaboration is really saying what it has done. So it's not claiming it's only mud and nothing else, but it's saying from all the accretion models that I have in my library, these models fit the best. Now, if you come up with another accretion model that the EHD hasn't tried, maybe this also fits the picture. Okay, but from all the accretion models that the EHD has tried, mud model fits best. Here I'm just saying, okay, what we see, is it connected to the photon ring? Is it a jet footprint? Is it a wall of a jet? So I can imagine that, I cannot turn this coffee, but imagine that the coffee is the black hole, and you have a jet which is empty inside, and the jet is giving the radiation. You could see also something similar, and you are even far from the black hole, and there is no photon ring there, there is nothing, and you cannot do any GR test or everything. So there are some ideas in the literature. I will stick to the super mud states for very high B accretion. I will say afterwards what this is. Also, this is another thing that till now we know that accretion goes till the event horizon, but I believe that there are different accretion modes that can go further out. Now for M87 that we were saying, this is an observation of M87, and this is exactly the base of the jet. So we have seen the base of the jet, I mean, we have seen also further, but even close to the black hole, the image is here, and then you have in a different frequency, I think this is 48 gigahertz or 46 gigahertz or something like this, you have this nice limb-brightened structure that you have the jet. Again, with muds, with different spins, 0.5, 0.937, whatever, the GRT, and then you blur it a bit, and you see that the high spin is the closer to the observation. So high spin mud fits the black hole shadow, fits the base of the jet. So from the accretion modes that we know, we are closer to this. Towards the last part of the talk, mud in 3D accretion continues through instabilities. As I was saying before, you have built a really strong magnetized funnel. Accretion, it's really hard to pass through this magnetic forest, but still it continues through instabilities. The efficiency of this process, how do I define the efficiency, is the power of the jet that I extract divided by m.c squared from the energy that goes to the black hole through accretion. And people have shown in 2011, Chekhovskoy et al., that you can get an efficiency of 140%, which they wanted to claim that now, okay, I get 100% from the accretion, but I'm taking out 140%. So the extra amount of energy comes from the spin of the black hole. I cannot see, these are not numerical relativity simulations, so I cannot change the space-time, so really change the spin of the black hole, but because I'm taking extra energy from the one that I put in my reservoir, this comes from the spin of the black hole, and I'm certain that this is a Bladford-Snike mechanism. So accretion continues. Here I want to show you new solutions that accretion stops. So you have this accretion around the black hole, but you have such a strong magnetized funnel, such a strong magnetized wall that accretion cannot pass through this wall. This is the equatorial plane, a slice of the equatorial plane. Okay, and you see that all this region is magnetized, and the magnetic field is fighting with the plasma. The plasma is trying to pass through, but it cannot for some time. Here, if you see the first row is the m dot, and for 3000 m, this cyan color here, you see that you have a minimum in m dot. So very few plasma is trying to reach the event horizon. So you integrate at the event horizon how much plasma flows inside, and you see that you have a minimum. And now in the last parameter here, which is the normalized magnetic flux, this gray line is the mud limit, which usually is 50 in a certain, let's say, values, but these solutions go to more than 1000 in the normalized magnetic flux. So you are almost a factor of 100 higher than the typical mud models. And now if you go to calculate the efficiency, which the efficiency of a mud is close to 100% and a bit above, you go to more than 10,000% for this for this time scale. And why this efficiency goes so high? I mean, you are only extracting energy from the black hole. You have managed to build a magnetized wall. Accretion cannot continue, but this huge magnetic flux from the Blunt-Force-Snelling mechanism working, you are getting a lot of energy from the black hole. And if you could allow for the black hole to spin down, I mean, to do really numerical relativity, you could see that the angular momentum of the hole would go down. And this is a small video of this solution. This is the equatorial plane. This is a colloidal slice. On the left is the density, on the right is magnetization. So you build this very magnetized funnel. Here is M dot in the first row, and below is the efficiency. So when you reach in M dot these really low values for such a long, you see that the efficiency is more than 10,000%. So this is the line of 10,000%. So you are extracting almost 100 times the energy you have from accretion. So accretion is negligible in this process, and it is only the extraction of energy from the black hole that really can be of interest here.
Yeah, I have several questions.
Yeah.
So, well, first, so now that matter is not reaching the black hole, something has to be happening with that matter, no? So it should be flowing out. So first question would be, have you checked that that all the material that goes in up to the radius where it also goes out? Because
if they do like this, you mean?
Exactly, because it should do like that, not by mass conservation. Because if that's the case, then one would expect that the outflows are very baryonic. Otherwise, so what we have normally in jets is that the inflow is baryonic and the outflow is mostly kind of a force-free jet, no? So it's nearly vacuum. But I think people tend to believe that the jets are like that, are almost vacuum, and there is very low baryon content. But if also the baryons are flying away, then that should be seen in jets.
Yes, but the baryons fly away, but this is the wind. You have a force-free solution at the black hole, because all this part is force-free, I mean. Like this. So all this part is, as you say, is electron-positron plasma. This is baryonic, and because you are far away, you will have always the wind, as you have in typical mass. You just change the structure of the solution. And even if this matter goes like this, which I haven't said, to be honest, again, you will have a wind. You will, I mean, at least from the velocities, you will not go close to relativistic velocities. You will have a wind as you have typically in match or in any accretions that you have a wind. Again, you have all this funnel, which is larger than the match solution, is force-free. So baryons cannot pass through this, let's say, funnel wall.
But still, there should be a lot more baryons in the wind, no? Because previously a lot of the matter disappeared behind the black hole, and now that is not happening anymore.
But this is, I mean, already before the wind is full of baryons. Maybe you mean the density maybe can be higher in the wind.
Right.
This, yes. Maybe you have a different density scaling. I haven't tried this. So if you, as you say, as you propose, I mean, if you integrate the density across R from the wind, maybe it has a different scaling. And this would be very interesting to see.
That would be very interesting to see indeed. And the other question that I had is, so this efficiency is calculated by the matter that processes or that goes to the event horizon.
Yeah.
But everything that is there currently is atmosphere. So, so the value that you get from the efficiency depends on the atmosphere value that you set. So it's very simulation dependent. If you lower the atmosphere value, then you will get a much higher efficiency.
Yeah.
But that means that this is not really a physical prediction. No?
So I mean, exactly what you say. I think that this is exactly, that's why it's a line and it's not variable. It's exactly the atmosphere. I agree. I try to argue that this is fake because of the, and I changed the floor velocity, the floor density, I mean, in 2-3 values to see the difference, and of course the efficiency changes. And I estimated a realistic efficiency if you assume a cold like Julian plasma to 4 million, I think, %. But yeah. But this is irrelevant. After some point, it's irrelevant. There is no point in discussing efficiency. It's just a black hole with magnetic field, as the solutions I was saying from 10 years ago. That this kind of solution exists. So in this type of solution, I mean, if I go that the disk is really far, there is no point to integrate them to the horizon and do the efficiency calculation because there is no end dot.
Right.
I mean, essentially from blood forest night, the efficiency can go to infinity if you connect it with accretion because it's purely electromagnetic effect and GR. These two ingredients, you don't need accretion. If somehow you have a lot of magnetic field at the black hole, you can have infinite.
And that
efficiency with respect to accretion.
Also, so this model then is very similar to the model by Blanford, where there is just a magnetosphere close to the black hole, and there is also almost no accretion of variance.
Yeah. So Blanford wrote this model for M87, but as an idea, it doesn't have a solution. I think this is the solution of his idea.
I see, because then my question was, how does he calculate the efficiency in that model? No?
He doesn't calculate the efficiency. I mean, he just have a drawing. I mean, at least this is what I've seen in a conference by him. He just have a drawing that, okay, my black hole is here, and I have here, he calls this ejection, this called whatever, that everything is flying away, and then the magnetic field is so large here that my actual accretion disk is here. I think this is what he is trying to say. That I have this big solution here, and because I have a lot of magnetic field, my accretion disk is further away from the black hole. But I think that his idea is a sketch. At least I haven't seen a computation. But yes, I think this is exactly his idea in a solution.
Right, that's very nice. Very
Maybe stop here, or okay, only 2 slides. Plasma is close to the black hole. Here is the black hole. It's just magnetic reconnection. When you have magnetic reconnection, I mean, you are giving energy from the fields to the plasma, and you have a lot of energy. Why would be this even more important close to the black hole? Okay, this is the BZ component that changes sign with the color, and this is exactly a current sheet of inverse polarity of the magnetic field close to the black hole. Why this is really important even in 3D? Because these can be really energetic and can give you flares, and you can observe. And these are physical also features that can go around the black hole, maybe can be important for Sagittarius A star. The last thing that I wanted to say, okay, another video, but maybe it's not the time for this. So at the same time that I was trying to do this plasmoids close to the black hole, Commission Asenio in 21, they say, okay, this is a different magnetic Penrose process that you have plasmoids born, one with negative energy goes to the black hole and the other with positive energy goes to infinity, and this is another totally different reason, mechanism than the Blanford's knife to extract energy from the black hole. And this is just a new paper with friends from Shanghai, and they see exactly this. This is the limit of the ergosphere. This is red is positive energy, at infinity blue is negative energy, and you see that a lot of plasmoids inside the ergosphere get this negative energy, and they actually plunge onto the black hole. You can see that you can have features with positive energy. But if I follow this plasmoid in time, so time goes from up down, you see that this plasmoid with negative energy is closing closer and closer to the black hole, and this will plunge into the black hole and will get some energy. So it will subtract some rotational energy from the black hole, and yeah, not spend more time for this. Okay, that's it.
Thanks a lot for the talk and for keeping time. We have time for one or two again.
Again, thank you for the interesting talk. So how important is the horizon? Meaning, if you have a sort of exotic object in an Virgo region, perhaps mimicking some of these circles that you mentioned that are important for the energy extraction, in principle, would be worse.
So I can tell you my opinion, because in the literature there is a different opinion, and people say that the ergosphere is the most important thing, and I believe that the most important thing is the inner light surface. So if you can have an exotic object that can mimic this inner light surface, because this is what you will produce electric currents in these field lines, and you will have an extraction of energy and jets like this, then I don't mind to have this.
Okay, the horizon is not fundamental.
The horizon is not fundamental, and actually, when Blanford and Snijek did the solution, they were saying about the Snijek solution. I don't know if you have ever seen these papers. So there were a series of papers that say it's really important the condition on the event horizon and how you play, and there is no condition there. It's just the whole equation on the event horizon. It's just an outflow electromagnetic condition, like we have in infinity. So, I mean, even initially, I was trying different boundary conditions at the event horizon or inside or exactly at the event horizon. The solution in the next grid point was the same. It didn't care about what is going on. It's like an inner infinity for the electromagnetic problem, the horizon. Everything was happening at the inner light surface.
I see. Do you know of any work already in that direction? That is, without the horizon, trying to...
The only work that I've seen, I think it's a Palenzuela paper that was doing some ergosphere things, but I don't remember. Like the ergosphere, it's really important. So now I don't have a black hole, but I have an ergosphere. I get it. So yes, it's the ergosphere, or something like this. No,
but in this context, or some other type of matter.
I don't remember.
Oh, maybe you can show me if you remember.
I don't remember.
So maybe, sorry, Hector, maybe before I will ask if there are questions on Zoom, maybe? Well, not Zoom, but online. It doesn't seem like it, so.
Just to follow up on the question by Carlos, one could say that it is possible to summarize this condition on the inner light surface as saying that as long as you have something that is like so it would be kind of a static limit for the wind speed instead of the light speed, then that would be sufficient condition to have this power project.
Can you say it again?
So the ergosphere is the, or sorry, this inner light surface.
Mm-hmm.
You mentioned that this is like the inner condition to have a powerful jet, not to have this inner light surface. But in the plasma, actually, one can the highest propagation speed is not the speed of light, but is the wind speed, and that's the. So if one could have a surface where that is similar to this. Not a light surface, but an advanced speed surface. That should also already be enough to have the.
Maybe, I think in these extreme situations, we believe that the alpha speed usually is close to the speed of light.
Right.
But maybe a correction, yes. Maybe what you say it's even more specific, but we have to see, I mean, how far it's the one surface from the other. I mean, in MHD solutions, they have this fast magnetosonic, and which really depend in the alpha speed.
So I was thinking on that because in that way, maybe your object needs to be slightly less compact than it would be. So maybe it is not compact enough to have an inner light surface, but if it is compact enough to have an alpha speed surface, then...
Yeah, maybe. But we have to define what is an alpha speed surface and if it exists in the problem. Because this pops up even from the equations. I mean, you just write down the equation and you see that the problem breaks there. There is a singular surface of the problem.
Unfortunately, many models of compact objects without the horizon, you can show that for the existence of the ergo region, there must be light. So they are actually ultra compact.
They are unstable, no? But
that is an ongoing discussion. But yeah, well, so both the ergo region instability and the one related to fixed deflections, it could be a source of instability. That's another thing. Because whatever you're doing in a fixed background. So
yes,
far, right?
Yes. And how do you check stability in these solutions? In numerical relativity or semi-analytical?
Well, some have semi-analytical arguments and perturbation theory. You can calculate modes, but some are tackled by numerical simulations, which is not very good to prove stability, but it's okay to prove instability if you trust me.
Well, then I think we can stop here. Let's thank Antonius again. So we have the group lunch now, so we meet in a second. And don't forget to tell Hector if you want to join for dinner tonight. There will be no seminar next week. We resume in 2 weeks.
Some generic mathematical argument for the local region instability in the absence of